Dear students, now I'm going to discuss about the problem in forced conversion, especially in flow over the spheres. So this is a external flow. If we discuss the problem, here the air stream at 25 degrees Celsius is moving at a velocity of 0.3 meter per second across a 100-watt electrical bulb. Bulb is at 125 degrees Celsius. If the bulb is approximated by a 60 mm diameter sphere, we estimate the heat transfer rate and the percentage of power lost due to the convection. Listen, so the given condition, the bulb is assumed as a sphere, that is assumed as a sphere, that is assumed as a sphere. Its diameter is 60 mm. So diameter is equal to 60 mm, which is equal to 0.060 meter. Now the air is blow over the sphere. Air at a velocity, so U is equal to 0.3 meter per second, and temperature Ta is equal to temperature of ambient, that is atmospheric air, is equal to 25 degrees Celsius. So which is a blow over a sphere at 25 degrees Celsius with velocity of 3 meter per second. And another one term, the capacity is given, a capacity of electrical bulb is given as 100 watt. Now we are going to find two terms. First one is how much heat that is lost by the sphere, that is called as electric bulb, to the atmospheric air. Second one, percentage of heat lost due to convection. I mean, from the 100-watt electrical bulb, how much amount of watt that is lost by means of convection. Okay. Now we can move to the problem. So find the solution. Here, first the problem is forced convection, as already discussed in the previous video. Because velocity is given, so we consider this as the forced convection. Then type of flow that is called as, that is external flow, because the flow is outside the surface, we consider that flow is the external flow. Then third one, we are going to find that is a film temperature, because in a case of convection, that is a flow over the spheres. Here page number around 130. So it's a case of external flow. External flow, it is a flow over the spheres. So in all external flows, you may be considered as a film temperature. There is a flow over the spheres. So in a flow of spheres or flow over the external surfaces, we may calculate the film temperature. That is a TF is equal to TW plus T infinite by 2, T ambient by 2. Here that is a T film temperature is equal to T of wall surface plus there is a T of infinity or TA by 2. Here the wall temperature, that the wall temperature is missing in the given, that is the wall spherical wall temperature, that is a TW is equal to 125 degrees Celsius. The air temperature is 25 degrees Celsius. So here 125 plus 25 by 2, you get in the film temperature, which is equal to 75 degrees Celsius. Now next condition, at a condition number 4, you are going to find properties at 75 degrees Celsius in HMT data book. So in HMT data book, you may find the properties. Again, we will move to the page number 40. Here the air is blowing, so we consider air. The air is blowing, you consider dry air. Here you need a property at a 75 degrees Celsius. But in the table, the 70 and 80 is given, so we need to calculate the 75. In a forced convection type problem, we needed three properties. One is nothing but the kinematic viscosity. Then next one is the Prandtl number. Then next one is the thermal conductivity. So we note it in a paper and we write in the presentation. So you have one is 70, another one is 80, we need a 75. So how we find the property values? So it's by means of interpolation. Here first we put the table. Um, we have on columns, we put a table. Here you can write the temperature values. Here it is a 70 degrees Celsius. It is 80 degrees Celsius. We consider this is the x term. So we call it as that is a x1. Here it is the x2. It is the x. Now we find the another property that is the kinematic viscosity. Then next one is a Prandtl number. Then next one is the thermal conductivity. For say, kinematic viscosity 70 degrees Celsius, that is a 20.59 into 10 to the power of minus 6. For 80 degrees Celsius, it is a 21.08 into 10 to the power of minus 6. Prandtl number which is equal to 0.694. Here it is 0.692. Thermal conductivity which is equal to 0.02966. Here it is a 0.03047. Now we are calculating the temperature for the given value of 75. How we can find the 75? So this is found out by means of interpolation. X minus x1 is equal to x2 minus x1 equal to y minus y1 divided by y2 minus y1. So here the y is called as, this is the y1, this is a y2. Here you are going to find y. Similarly y1, y2 you are going to find 1, y1, y2 you are going to find y. So it's a simple strategy. Here x minus x1, here x is equal to 75 minus 70 divided by 80 minus 70 equal to, for solving the first one kinematic viscosity, y minus 20.59 into 10 to the power of minus 6 divided by 21.08 minus 20.59 into 10 to the power of minus 6, because 10 to the power of minus 6 is common for all things. So that's why I introduced this terms. So this is the common for all the terms. Here it is equal to that is equal to 5 divided by 10. So it is equal to what? 0.5 equal to y minus 20.59 into 10 to the power of minus 6 divided by, you have some term that is equal to 21 into some, that value is given 21.08 minus 20.59 into 10 to the power of minus 6. So this is the one equation. So left hand side, that is a 0.5 you fix it. So you can substitute the appropriate values. That's appropriate of, you can get the finally, that is y is equal to, that may be around 20.34 into 10 to the power of minus 6. So here you can write that is y is equal to 20.34 into 10 to the power of minus 6. Similarly, next you are going to find the Prandtl number calculation. So in a Prandtl number calculation, you can use the another step, because in a Prandtl number calculation, the left hand side remains x minus x1 and x2 minus x1. Left hand side remains common for all the cases. So again 0.5 is equal to y minus y1 in the case of Prandtl number 0.694 divided by 0.692 minus 0.694. So after the substitution, you may get the Prandtl number is equal to 0.693. Similarly, for thermal conductivity, this is for Prandtl number. The next for thermal conductivity, say same, the left hand side x minus x1 x2, because these are common for all the parameters. So the remaining right hand side parameter get varied. So 0.5 is equal to y minus, what is the y1 here, 0.20296 divided by 0.03047 minus 0.02966. So after the substitution, you may get the thermal conductivity as values nearly 0.03065. Then we require this property for this particular statement, promise statement. Then we find the properties for a fourth point. Next, fifth one, we are going to find the Reynolds number. Reynolds number. Already you know the Reynolds number is equal to U d divided by nu. The velocity is given. The velocity that is equal to 0.3 meter per second. Diameter is 60 mm, and the nu you can find out this is 20.34. So substituting the appropriate values. So 0.3 into diameter 0.060 divided by that is a 20.34 into 10 to the power of minus 6. We can get the Reynolds number which is equal to 884.95. 884.95. So which is equal less than 5 into 10 to the power of minus 5. So the flow is considered as a laminar. Then next sixth step you are going to find the Nusselt number. Then sixth one is Nusselt number. So in the Nusselt number again we move to the data book around page number 130. It's a external flow. In external flow we have a flow over the spheres. In a flow over the spheres, so it's air for various ranges of Reynolds number between 17 to 70,000. But in our case, we have a Reynolds number is equal to 884. So exactly suitable for this condition. So better we take a Nusselt number is equal to 0.37 into Re power 0.6. We have to evaluate the properties at a TF. Already we done all the properties at a TF. That's for gases. It's a common form. Here also we can move some other condition, but the Reynolds number is too much. That is, it is greater than what? 3 lakh and it been in the 5 lakh. So this condition is not ever satisfied. So this condition is given, but it is given for liquids. This Reynolds number is satisfied, but it is given for liquids, so it is not valid. So we consider this one is suitable for our condition. So Nusselt number, there is Nu is equal to then 0.37 Re Reynolds number for the particular diameter power that is 0.6. So sorry 0.37. So 0.37 into Reynolds number you find 884.95 into whole power 0.6. Then you find the Nusselt number which is equal to 21.69. Then after finding a Nusselt number, we are going to find the heat transfer. Then seventh one is equal to that is a heat transfer. So from a Newton's law of cooling, you know that there is a Q is equal to that is HEA is into delta T. So A is equal to surface area. Here before the Nusselt number, you are going to find the heat transfer coefficient that is called the seventh step. That is the seventh one is equal to that is a heat transfer coefficient. Heat transfer coefficient. So H is equal to a Nusselt number is equal to that is called as Hd divided by K. So H is equal to Nusselt number into K divided by that is a D. So Nusselt number is equal to 21.69 into K that is already defined 0.03006 divided by diameter 0.060. Then you find the H value that is equal to 10.87 watt per meter square Kelvin. Then after finding the heat transfer coefficient, we move to the next step that is 8. This is the 8th step that is called the heat transfer. So H is equal to 10.87. Here the surface area important factor this is a sphere. So the surface area of sphere is equal to that is a 4 pi r square into delta T which is equal to wall temperature minus ambient temperature TA or T infinity anyone. Here 10.87 into 4 pi, the radius is equal to 0.030 whole square into wall temperature is equal to 125 and ambient temperature is equal to 25. Finally, you are getting heat after the heat transfer after the capital substitution. You are getting the heat transfer that which is equal to 12.29 watt. 12.29 watt. This is a heat transfer for this case. Then after finding the heat transfer, we move to the next condition. What is the next condition? How much amount of heat transfer? Percentage of heat lost by what? Convection. Convection. Here, the input of bulb, there is a bulb having an input of say 100 watt. So out of 100 watt, how much heat is lost by convection? So the heat lost by convection, that is equal to 12.29 watt. So this is called as the given, this is the lost. So finally you can get the percentage of heat loss is equal to percentage of heat lost is equal to 12.29 divided by input, that is 100 into 100 percentage. So finally you can get there is a 12.29 percentage of heat loss that is made by convection for bulbs having a capacity of 100 watt. Then air is blowing at the temperature of 25. This is a bulb 100 watt. So finally heat loss by convection is equal to 12.29 percentage. If the surface temperature is 125, then air temperature is surface temperature 125, the air temperature is 25 degrees Celsius. Okay, thank you. If you have any comments and any remarks, please include it in the comment section. Thank you.